Okay, I'll do a bit of waffling while I wait for the hardware to catch up, okay? I'll blame Bill Gates for this one. What we've done so far is we've introduced the idea of a frequency response and this idea that linear systems, if you put a sinusoidal input in, we get a sinusoidal output out. It can be a phase shifted sinusoid and it can be different in amplitude. And we've investigated ways of describing that, if you like, by introducing things like, particularly for us, the Bode plot. Okay. We then explored last week, I think, the relationship between a transfer function and the Bode plot. Okay. The idea with that being that we could actually now go in either direction. If we get experimental data, then we can produce a Bode plot, and from that Bode plot we can evaluate a system's transfer function. Okay. Similarly, if we've got the transfer function, we can sketch the Bode plot. We can draw the Bode plot from it. So we've got a tool that works in two directions. Okay. So what I'm going to do today, if the computer ever fires up, is a couple of things. I'm going to just extend that a little bit further to answer that question that every student has in the back of their mind, sort of, yes, so what? What can we do with that information when we've got it? Okay. So I'm going to introduce to you some ways of modifying the behavior of these systems. Okay, let's see if this is warmed up yet. Okay, finally, we're there. Okay, next thing we're going to do is modifying behavior. So as I said, we're looking at frequency response information. We've worked out the relationship between experimental data, transfer functions, how it shows up in the frequency domain. And I think also we introduced this idea of gain and phase margins, which gives us a tool that we can use open loop frequency response behavior and information to predict what would happen in the closed loop. So, okay, what I'm going to do today is let's start thinking about using these techniques to modify system behavior. This is chopping off about the top 1/8 of my slides, unfortunately. That's probably not the interesting bit. So we're going to use frequency response from open loop data to produce appropriate control strategies in the closed loop. Okay, and this is the slide you saw last week, just to refresh your memories about what the gain and the phase margins look like. And here again is last week's slide just to describe them. Okay, gain margin is that little bit of additional gain that's required to make the system just unstable. We're looking for this -1 number on the open loop. Phase margin, similarly, is how much additional phase lag can we put into a system to bring it to that point of just about unstable. Okay, so those are the numbers that we're looking at. So we understand, well, I understand, your line's missing. We understand how to use open loop gain and phase margin as a predictor of closed loop behavior. So let's see about modifying it. If the prediction gives us something that we're not happy with, what can we do? Okay. Now, a simple approach, if you think about it, is if you just think of the amplitude plot, okay, we're looking for gain and phase margins, but simply by introducing a gain term into the open loop, I can move that amplitude plot up and down. Okay, so simply introducing a variable gain and forward path allows us to change the margins. And here's a very simple one. Effect of reducing the gain in this case, the original plot of the original data, if you like, is the green one. And you can see that the old phase margin is up here. It's modest, it's okay. And the old gain margin up there is again fairly small. All I've put in there is I've introduced a gain of less than 1. So gain is a little bit of a misleading word because I'm making things smaller, not larger. And by reducing that gain, I've just brought the amplitude plot down, okay, to give me the blue line. And you can see what I've done by doing that is if I've made the gain and phase margins much bigger. Yeah, so the new gain margin is, well, it's probably nearly double what it was, And the new phase margin is considerably bigger because it's over here. Okay, and all I've done to achieve that is to put in a gain of, I forget the numbers, I'm afraid, it's something like 0.5. That's the easy one. What else can we do? Well, we can get a bit more sophisticated with all this stuff. And instead of just crudely lifting one of the curves up or dropping it down, we can introduce more sophisticated techniques in the shape of what we call compensators. Okay? And these are devices that you put in just the same way as we would that gain. Just put them in the forward path so they appear in the open loop transfer function. Okay, and I'm going to talk about 4 different sorts, really. And then pick one as an example and work through with that. And these are typical compensators. The first one is a lead compensator. The second is a lag compensator. And then you've got a lead lag, which is a combination of the two, and a lag lead, which is also a combination of the two that you can figure out for yourself. So these are standard compensators that we use. Okay? And there are standard design techniques for working out what the numbers should be. Now, unfortunately, or maybe fortunately, we haven't got the time in this module to go into the design techniques using these things. So what I'm going to do is I'm just going to talk you through typically how they might work. Okay, so let's have a quick look at the lead compensator as an example. Okay, again, apologies for it chopping off the top. The lead compensator, I'll have to, no, I can't drag that down now. If you look at the lead compensator, all it is, it's a first order lead, 1 plus S upon A, followed behind at a higher frequency by a first order lag. Okay, so alpha is bigger than 1, which means that the corner frequency for the lag becomes afterwards. It's at a higher frequency. So what this thing is doing is introducing a first order lead. And if you think of the amplitude plot, that's going to start, the gradient is going to be positive, it's going to go up. And a short time later, it's going to level off again. Okay. More interestingly, if you think of what's happening on the phase plot, we're introducing a bit of phase advance because of the lead, and then we're taking it away again. Okay, put some example values there. What does the compensator frequency response look like? Well, it looks like that. Okay. The top of the slide just says, it just gives you the example transfer function where I've got a first order lead with a corner frequency of 10 radians per second, followed by a first order lag with a corner frequency of 100. Okay, so what this gives us is the ability, and in a sense the phase is the important one, to pop in a quick lump of phase advance where we need it. Okay. There is an effect on the overall gain, but we can do some interesting things just by introducing that phase advance. Yeah, does that make sense? Okay, you can see how this is built up from a lead and followed by a lag, and that's a lead compensator. There's absolutely no prizes at all for guessing what a lag compensator looks like. All you do with a lag compensator is you make the lag corner happen first. So instead of going up and leveling off, it goes down and then levels off. And the phase bump that you can achieve with a lag compensator is negative. Okay, but as a tool to adjust our to adjust our Bode plots, they're really good. Anybody care to guess what a lead lag compensator is? It's one of those followed by a lag compensator. So what you can do then is you can achieve a positive bump in the phase angle followed by a negative bump. Okay, and all these things allow you to modify the bode plots. Okay, cop-out slide. Okay, by now, you've spent at least 2 or 3 tutorials sketching out bode plots for all sorts of transfer functions and all the rest of it. So by now, you should be able to sketch the bode plots for these compensators yourself. Okay. Have a look at them, make up some numbers, and use that as practice for your bode plot sketching. Okay. So sketch for yourselves the bode plots for these compensators and what their effect might be if added to a system overall frequency response. Make stuff up, make up a system, look at what a compensator will do when you add it in. Right, at this point I let myself down with the technology, so from here on there's a couple of errors in the slides, okay, which I will correct before I update them on Blackboard. First error is I couldn't get the scanner to work, so the picture is missing from this slide. Okay, so, but it's okay. There it is. I'm struggling with the technology today, aren't I? That is an unmanned, free-swimming, submersible vehicle. Okay, sort of thing you'd use in exploration. So they usually carry things like sonar equipment and all that sort of stuff. You can see what it is just basically a fairly efficient shape. It's got a propeller at the back and it's got control surfaces. It's got elevators and it's got rudders and all these kind of thing. Okay, so this is an unmanned, free-swimming, submersible vehicle. And what I'm going to be looking at, just to talk through the use of compensators, okay, is the response to changes in pitch angle. So we've got these elevators, if that's the right word for them, I'm not sure, on the back of the tail there, and we're going to look at the relationship between the pitch angle of the vehicle and our input into those actuators. Okay, got any aero students in? Yeah, pretend it's not water, okay? You'll be fine. Now, again, to take some shortcutting past my rubbish use of the technology, I happen to have a set of open loop frequency response data for that vehicle. Okay. I'm going to skip over the next bit because you know how to draw the plots. But basically, you've got a whole set there of information about the open loop behavior of this device. Why am I interested in that? Well, fairly obviously,
PC selected.
If it's going to let me. Okay, so what I'm looking at is the output, which is the pitch angle of the vehicle, theta, to the elevator surface angle, delta E. From that experimental data, I can construct an open loop bode plot and have a quick look at the gain and phase margins. Okay, gain margin is very approximately 20 decibels. Phase margin is about 50 degrees. In the context of this device, those numbers are actually fairly small. So we've got a fairly small margin of error, if you like, or a fairly small margin. So I would expect this thing to give me a stable behavior in a closed loop, because both margins are positive, but I wouldn't be surprised if it's a bit oscillatory, because the phase margin is, I don't know, 60 degrees or so, which isn't enormous, so I would expect some oscillatory behavior. And there it is. A bit oscillatory. Not very fast. Don't know what the 5 is for. That's probably just poor typing. So this thing's step response would be, I don't know, it reaches that first peak at about 11 seconds. So it's not a fast system, but it does overshoot. Okay, now what I'd really like to do, I think, is I would like this is a closed loop time response, okay? I would prefer, I don't really mind that this is slow. I can live with that because, it's not a fast moving vehicle anyway. I'm a bit disturbed by the overshoot. If I use the normal sort of just putting in more gain or less gain approach to reduce that overshoot, it would also slow the system down further. Okay, so I'm not happy with that. So what I'm going to do is I'm going to very quickly run through, well, not too quickly, but going to run through an approach to designing this thing using, or changing that behavior using a lead compensator. Okay. Now, as I say, we don't have time to go through the design process for the compensator, so I'm just going to give you some numbers that work. This is the bit that's wrong. Okay, so apologies for that. I'll explain how it's wrong in a minute. This is actually the open loop Bode plot for that submersible. Okay, so we've got the data, we can look at the data, and we get that oscillatory response. The reason that Bode plot is incorrect is I forgot this bit. Okay, oops, wrong direction. That 2 over s plus 2, when I cut and pasted cheerfully the other night, just popped these in, I'd forgotten to put in, this is the transfer function for the actuator for the elevators. Okay, so if I'm closing the loop, I need to have this in place. This is the actuator. Okay, so I will clean this up before reposting it on Blackboard. The version that's currently out there doesn't include this anyway. Okay, so apologies for that, especially for those of you that I know some of you take the trouble to print them out to follow the lecture. So let's move on. Right, I'd like to redesign this and use a compensator. So we go through the whole compensation process that I'm not telling you about, and out pops this thing, which is some kind of compensator. It is in fact a lead compensator. A couple of things to notice about this. It's not immediately apparent from the numbers there, but if you work that out, it's actually got a steady state gain of 1. Because if you go 19.77 times 0.25, you'll get back to 5.11. So it's actually got an overall gain of 0 dB in the steady state. Okay. What sort of compensator is it? Well, just told you really, it's a lead compensator. Puts in some phase advance between the 2 corner frequencies. We've seen the picture. Right, that's the system we're starting with. This is the correct slide for our system. Okay, forget the extra gain words. But this is our Bode plot for my submersible with the correct actuator on the elevators. Okay. Let's have a quick look at things like phase margins and gain margins. Well, 0 decibels is about there. At that frequency, what's the phase shift? Well, I've got enough room for about that much extra phase lag. Okay, so that's my measurement of the phase margin. Similarly, where's minus 180? Well, there's minus 180. At that same frequency, I've got a little bit of gain margin. Yeah, it's that simple to find them. Right, so let's see what the compensator looks like. So the blue one is our system, which is the submersible and its actuator, the open loop transfer function. And through the magic design process I'm not telling you about, I've decided that my compensator is represented by this green line. Okay, that transfer function that was given a couple of slides ago. And you can see it's doing all of those things that a lead compensator should do. It's kicking up the amplitude a little bit, and it's providing a bump of positive phase angle. So what happens when I combine the compensator with the system? Well, then we get the red one. Okay, and you know now how to deal with Bode plots, how we add pictures together, and the red line there represents the compensated system. Okay, you can see fairly easily what's happened is the blue one, the system standalone, The gain's been lifted a bit at high frequencies, but more interestingly, what we've done with a phase plot here is you can see we've put that big bump in it, and we've put that in there just about where we're concerned about gain and phase margins. Yeah, you okay with that? Just adding this extra bit in. That's the new closed loop time response we get. Spot the difference. Why is that? Well, this has lost some of my slides, unfortunately, so I'm going to have to scribble some more. If we look at this thing and we try to look at what's happened to the gain and to the phase margins. So, looking at the compensated system, it passes through 0 decibels at a little bit higher frequency than it used to. Okay, because we're already seeing the effects of that increase in gain, it's lifted that curve up a little bit. So in a sense, we're pushing that frequency at 0 dB, we're pushing it a bit higher. And I would expect that to be a bad thing. Because typically phase curves come down this way. By pushing that way, you'd think that I'm going to be reducing my phase margin. Thankfully, the effect of this bump on the phase is greater. So the fact that we've moved up by a reasonable amount of frequency there to the right is more than compensated for by, that's the blue one, wasn't it? And that's the red one, by the difference in phase. So my original phase shift, the blue one, is about that much. My new phase margin, beg your pardon, my new phase margin is actually quite a lot bigger. Let's see if I can clean this up. Okay, so I'm now up to, well, it's actually over 90 degrees of phase margin. Okay, whereas it was 50 or 60. So I've got a much increased gain margin because of that. What's happened to the phase margin? Well, identify when the phase shift is minus 180, and in the original system, it's about there. Okay. At that frequency, there's the original gain, and there's the original gain margin. Okay, which is, it's not enormous. In the compensated system, what's happened is that because of that big chunk of phase lead we've put in there, we have pushed up the crossover frequency, the frequency at which we hit minus 180, quite a lot further up the frequency band. So then at that frequency, despite the fact we've got additional gain coming in, because of the way the compensator works, because we've managed to push this frequency up so much, my gain margin certainly hasn't got any worse, has it? And in fact, it's probably a fractionally better looking at that picture. Okay, so all of these things are to do with compromise. Okay, the fact that we're putting in more gain, generally speaking, isn't such a good thing for stability in a closed loop. But the fact that we can fill in this big lump of phase lead, I can use that to compensate for it. Okay? Then after a while, of course, when the effect of the lead goes away and my two curves are matching again, I've got the blue and the red coincident in there. I'm stuck with this extra gain, but we're already on that part of the slope where things are all diving down here. We're all on negative gradients. So to some extent, that becomes less important. But we've managed to give ourselves this big big lump of phase lead just where we need it. This is me. I've got my final values conserved. I didn't draw your attention to it, but it was 0.8 in the first slide. But what's nice is I've managed to reduce that overshoot. I'll put the original one up as well. Okay. The blue one is the original closed loop time response. The green one is the one I've ended up with after designing and putting in my compensator. So you can see, what have I done? Well, I'm maintaining pretty much the final value, 0.8. That's what I was targeting. That's in place, that's fine. But what I've managed to do is I've managed to reduce that overshoot down from, I don't know what it would be, probably heading on for 15%, down to something more like 4. Okay. And what's nice about this technique is I've managed to do that without slowing down the process. You'll see that the time at which it first reaches the final value is, is not much different. The compensated one is very, very fractionally slower when it first hits that 0.8. Having said that, its initial performance here is much faster. Okay, so the initial rise is very much quicker. I've managed to kill the overshoot quite considerably, and even the time of the peak overshoot is only very slightly slower. Okay. So if you look at those responses and think of the terminology from when we're talking about time responses, thinking about things like rise time, settling time. Okay. The rise time, to be fair, isn't very much changed. Because the rise time really is about this first bit, isn't it? Between 0 here and 0.8. That's the bit where we're concerned with the rise time. So that definition, I haven't managed to change that very much. The settling time, I would argue, is massively improved. Because if you remember the definitions of settling time, it's the time it takes to get to and stay within 5% of the final value. Okay, and because I've managed to kill that overshoot, once I'm there, I'm within that boundary. So I've managed to make an enormous improvement in the settling time for this. Does that matter? Well, depends on the context, really. This is an underwater submersible sort of vehicle. We haven't gone into detail about what it's for. If it's got some kind of equipment on board where it's important that it's pointing in the right direction, which could be a camera or something like that, it's the settling time that matters. It's the time at which we can say, yes, that's pointing in near enough the right direction, plus or minus 5%, we can now take the picture. Or it could be something more offensive, like a weapon. I don't think that device is. So we've managed to introduce a compensator using a standard pattern. I picked on a lead compensator for this exercise. If you wanted to design one, you go into the compensator design books and there are sort of off-the-shelf formulae for how to do it. So that gives you the numbers to put into your lead compensator. Okay, so it's a very straightforward design process. Implementing the compensator, well, a number of ways of doing that. Again, it depends on what it is you're controlling. You can implement a lead compensator very easily in software. Okay, so if this device has got a software loop somewhere in there between our demand, you can implement a lead compensator in software. You can implement a lead compensator just as a simple piece of analog electronics, or indeed digital electronics if you want to go that way. There's all sorts of ways of doing it. Okay. But this is one of the first examples of kind of an off-the-shelf controller. And we can do all sorts with it. So, what's going on? Having identified gain and phase margins, which by now you understand, using the open loop frequency response plot, we've got a number of tools at our disposal, okay, to modify those parameters. We can use a simple gain. We all know, just putting a gain in there, we can move the amplitude plot up and down to suit ourselves. We can use that to modify the gain and phase margins. And as a very broad sort of statement, typically if you increase the gain, you'll reduce the margins. That's how it works normally. So typically you increase the gain, your systems become more oscillatory. Depending on the system, if you increase it enough, you can push that system into instability. Okay, so the gain is there are some things you can do with it, but it's sort of limited really. So we introduce these more complex compensator patterns. Lead compensators, lag compensators, and then ones that are a combination of the two, lag lead and lead lag. Okay, and what we can do with those is to do some more specialist modification of that frequency response plot. Typically by looking at what's happening in a phase plot and moving things up or down to suit ourselves. Okay. As I say, this module, we don't have time, unfortunately, to cover the detailed design techniques for these, but you will find it in any decent control text. Okay. It's a bit of an old text now, but I just still happen to have a moth-eaten copy on my shelf. For example, Control Systems by Sinha has got a really nice chapter on if you want to achieve this, then you choose this kind of compensator, and then it goes through the design techniques for finding the values for the compensator. Okay. We're not going to do that simply because of the pressure of time, but you need to know that that stuff is available and out there. And frankly, it's not that difficult. It's, you know, these techniques, they've been refined over the years. It's almost a case where it's plug in the numbers and you'll get the right response. Okay, does any of that make sense? Doing well, 3 nodding heads, excellent. Okay, so what we're trying to do, putting it very crudely, all we're doing is we're finding ways to move that bowed phase plot around to suit ourselves. Okay, and to suit ourselves, to give us the sort of time response that we want. Okay, I think I'll stop there. That's probably enough, isn't it? Next week, I think we're going to move on a little bit from frequency response. So we've looked at it now for 3 or 4 weeks. I can't remember how many exactly. Make sure you're comfortable with the frequency domain, okay? Because we're going to have to move on. And if there are still areas that you're not certain about, you know, bring them to our attention. Whichever tutorial group you're in, just grab the tutor and ask them just to clarify, because we do need to move on. Okay, thank you very much.